Hey, welcome back everybody. We are here at the Humanoids Summit, the inaugural Humanoid Summit here at the Computer History Museum in Mountain View. We're excited to be here. You know, I think it's the largest single collection of humanoid robots that's ever been put together. So we're excited to be here and get some of the founders and some of the people that are really making it happen. And this is one of the most exciting robots out there. You may have heard of it. It's Neo. It's the predator, or the successor to Eve. And we've got the founder and CEO. He's Bernt Børnich, the founder and CEO of 1X. Great to see you.
Great to be here.
Congratulations on the keynote. That was really helpful.
Oh, thank you. Glad you liked it.
Yeah, absolutely. So let's get into it. You've been doing this for 10 years, you said, since you started the company. A long way from the beginning. But you started out with the motors and you made some really interesting decisions early on that you wanted to be vertically integrated. And you talked a little bit about motion. I don't think most people think of this from kind of a motion perspective. How important is motion and why did you choose to start with that fundamental building block, which is the motors?
Yeah, I think like if you look at any video of nature, right? It doesn't matter if it's like a human gymnast or a cat running or whatever, right? You see there's this beauty in how animals in general move and the dynamics of animals. And this is not an intelligence challenge. This is about the dynamics in that biological system. And there are a lot of like first principle, just from physics, that actually governs this. And I feel there are two paths in robotics. It's the classical path where you say, we're going to ignore all of that, and we're going to try to make it in software. So you could say like, a good example is an industrial machine, like an industrial robot.
Right.
It's a big, heavy machine, so it's inherently quite dangerous. But if you add a lot of sensors to it, you add brakes and all these things, and if you have a controller that is very, very fast, then maybe you can somehow layer safety on top of it, right? So it's like if I accidentally hit the table, I need to stop fast enough not to break the table. And maybe if I have sensors and I'm fast enough, I can do so. But that's not what we do. Like humans, we are just inherently super low energy. Everything we do through our life is a collision, right? So when I pick up this bottle, I'm actually colliding with it. If I put my hand on the table, I'm colliding with the table. If I take a step, I'm colliding with the ground. And I can do this in a very stable manner, very low impact, not really dangerous to myself or the environment. And this is because there is so little energy in me when I move. And this gets deep into the physics of it.
Right.
But trying to say this kind of in layman terms, when you have a robot joint, it's like if you pretend I'm a robot, right? And I'm moving like this, inside me, there is nothing that moves faster than my arm. In a robot, you would have a gearbox here. And there would be a motor inside here that spins, let's say 100 times as fast as my arm is moving. We spin at like 10,000 RPM. And if you do this, we humans, we actually have great intuition on this. We know there's a lot of energy in that system. Because if I tell you to stick your finger into that system that's rotating at 10,000 RPM, you will say, no way, right? You know what will happen to your finger.
Right.
Yeah? And we learned this in school, right? A car that goes twice as fast is not twice as dangerous, it's 4 times as dangerous. Because actually, the energy in the system scales with the velocity or speed squared.
Right.
Yeah. So this is why robots are dangerous. They have huge gear ratios, means they have spinning weight that spins very, very fast. And you can think about it, there's something spinning at 10,000 RPM, and when I hit the table, it needs to stop. There's no way that can just immediately stop. It needs to spin down. And that's why a robot would normally crush the table if it hit the table.
Right.
So for robots, we say they collide. But we have a term for it in the industry. My robot collided. Right? Humans don't collide. We just interact with the world. Sorry, so that's a long tangent. But
right.
To me, that's like the fundamental problem in how to make robots useful outside of a factory. You have to be able to do safe interactions. It's safe with respect to just stepping on the ground. It's safe with respect to accidentally touching you. It's safe to respect the ball when I pick it up. And this is not an AI problem. This is a hardware problem. And this is why we started with the motors, because if you have very strong motors, then you don't need the gears to be strong enough. And now you can pull tendons kind of like how human muscle work.
Right.
And you can create your motion through this. And that's why you can see when our robots move, they move very differently from all other robots. It just looks human, it looks natural.
Right.
But it's not because it's going to look great. I like that it does that, but that's not why we do it. We do it because we want it to be capable and still safe.
Right.
So we can integrate them into society.
It's interesting that it's both for the kind of the biological feedback and what it looks like and how it moves so it's comfortable, but also for the safety, because I don't think a lot of people, unless you go to a job at an auto factory or something, really remember that a lot of the robots, industrial robots, have big taped areas around them. You know, you don't want to enter the sphere of that robot's influence because you can really get hurt. So safety is a really #1 kind of design priority with bringing these things into the home.
Clearly, and then it's actually even deeper than that. Because if you look at collaborative robots, then you're trying to fix the safety aspect through saying that if I detect that I touched something that wasn't planned, I will stop. I will like put on the brakes and stop the system. It's still not quite safe because the initial impacts are a bit high, but the problem there is that that enables you to have robots that can work next to humans, not together with humans. Because if anything happens, the robot stops. And that doesn't work if you want to just generally have robots among us doing everything in society together with us.
Right.
You need to be able to softly interact with people.
Yeah. Now, one of you guys have a very clear mission for the company, to create an abundance of labor. And we've seen all the demographic data. You know, there's negative population growth in a lot of the development worlds. I think I saw that population is supposed to peak in about 6 years and then start going down. To think of a world of an abundance of labor is pretty magical to even think of. How did you get there, and how do you keep that as your North Star in terms of figuring out where to set your priorities?
It's actually a very good question. I think this is one of those things that takes a while to like mature, because as I grew up, and I've always been like passionate about technology, building things, it took me quite a while to realize how important energy is, like how much the world is governed by access to energy, and how as a society, we're mainly defined, like the productivity of our society is mainly defined by our access to energy. The second part of this is labor, and how we turn energy into labor. That took even a bit further to figure out, but like, in hindsight, this is completely obvious. But like, it's just like, as a society, we are the ability to harvest energy, which we're pretty good at. And I think if you ask someone from the 1800s, you said like, hey, in 2024, you can buy a kilowatt hour of energy for 10 cents, they would think you were out of your mind. Like, that's going to take 1,000,000 years, right? It's kind of like if you look at like the last thing that was written about the Wright brothers 3 days before they started flying, was that it would take the combined force of all mathematicians in humanity 1,000,000 years to solve this problem. That was what academia thought. And then 2 days later, the plane takes off.
Right,
so,
right.
But anyway, I'm going on a tangent here. But point being, it's very hard for someone back in that society to imagine that energy is just almost abundantly available and free. We can still get better at this, but I think as a society, we've gotten pretty darn good at harvesting energy. What hasn't happened yet is that we've figured out how to turn that into products and services. That's still mainly done by people eating corn and then converting that into mechanical energy and making products and services. Once you can take that energy and just turn it into any product and service that we then can consume, that's the next step of society. And I think looking back from this, a few years from now, if you grew up in that society, you will kind of like, it will be unfathomable to you that like there was a world before you had access to labor. Like, how did that world work?
Right.
Just that we think it's very weird to think about like, oh, we didn't have light, we didn't have heat, we didn't have like all these things, which comes from energy. But it's always easy to look back, right? And it's hard to look forward. But it is going to change the world, I think. Equally impactful to some of the big things, like you can say like agriculture, printing press, car, computers. It's a huge shift, and it will redefine humanity and how we live, but hopefully in a very, very positive manner, where we can all have everything we want and still be a civilization that is sustainable. And I think that's something that also often doesn't get mentioned enough, how much sustainability is a function of productivity.
Right.
Because if you have infinite labor, there is no reason to cut cost, no reason to cut corners. You can do everything in a sustainable manner. And I think the path to a sustainable planet does not come through saving. It comes through actually enabling you to do all of these things in a sustainable manner.
Right. Well, it's interesting on the exponential curves. I did an exploration of a Cray supercomputer from the 70s to your modern smartphone. And there's a lot of crazy metrics in terms of the storage and the memory and the CPU, but the piece that most people miss out on is the energy consumption. And those Crays took as much as 3 houses for a month compared to your smartphone, which uses watts when it's sitting still, and I think like 12 watts or something when it's working hard. So the efficiency in terms of the productivity per unit energy is the piece that's pretty exciting. So you've been at this for 10 years. I mean, what have you seen in terms of the exponential curves and the opportunity to go from your first robot, Eve, to Neo, and how the opportunities to bring so much more power and smarts to bear economically than even just a simple 10 years ago?
Yeah, I think like back to the motors and actuators in general, and like how the robot moves. It's kind of like, almost like a Moore's law kind of thing here in how we're able to create more and more force-dense motors and actuators, and roughly doubling this, like it's not every year or 2 years, it's every 5 years, or more 4 years. Roughly every 4 years, we're like able to double this torque density. And this is really what enables completely new paradigms in robotics. So 10 years ago, before we did this, if you were going to build a robot, you would have to use a very heavily geared system. And this means you would have a stiff, kind of dangerous, heavy robot that's expensive to manufacture. And for Eve, our first product, that's the first time we actually managed to do this in a more bio-inspired manner and get all the advantages of that across everything from safety and capability all the way to manufacturing with respect to cost. And then, of course, the second generation Neo is just so much better, right? It's not even comparable. So the original Eve is almost 90 kilos and a bit weaker than most humans. Neo is 30 kilos and stronger than most humans, while still keeping the same like safety and dynamics and everything. 30 kilos means safe. 30 kilos means cheap to manufacture, right? It's all about the material cost. And I'm super excited to think about what comes after Neo. Right. I can't disclose anything yet, but we have pretty good plans on what also comes after Neo. Because to me, Neo is kind of like the iPhone 1, right? And every couple of years, there will be iterations, which in the beginning really moves the needle. Right. And at some point it will start to plateau, but we're not at that point anymore. Right. We're not at that point yet. We're at the point where like every generation is just immensely better than the previous one, not just on the AI, but also on the hardware. Right. I think that's a very interesting journey.
Right. And the scale, right? We've seen it in electric automobiles, and having car scale in a lot of those technologies really changes the game. So the robotic scale in terms of what you guys are doing, humanoids, is still very, very small. But let's shift gears and talk about the home environment.
Yeah,
so go ahead.
Before you go there, I just want to comment on that. It's a very good call out about scale, because humanoid robots are actually a product that only makes sense at scale. Most people, it takes some time for this to sink in, but like, this is like a PC, right? In the beginning, you had mainframe computers.
Right.
But actually, it took off when you got the PC, and you get this huge amount of volume, and you get this ecosystem. But when you are sitting here with your computer and you're like writing something in Word, man, is that a complicated machine to be able to write something. It makes no sense, right? It's so complicated to just be able to write something. But it's still the cheapest device to write something, because it's produced at such a scale that the quality is so high, the cost is so low, the ecosystem is so big. Humanoids is exactly the same. It only makes sense at scale. And that's why this is really all about, it's about cost and manufacturing, right? You need to get to scale for the product to have like it's right for existence.
Right. Well, and you just get the R&D effects too, right? I mean, you take it, sensors and what mobile phones have done to the sensor world in terms of magnetrons and cameras and all these things now are so cheap that then we see them integrated in all kinds of new ways and new applications. So scale matters. So the home environment, very different. Most people are probably familiar with robots that they see in car factories and the big industrial arms. The home is a really different environment, and you've built a really different type of solution. So talk about what's unique about the home, what excites you about the home as an environment to deploy Neo.
Yeah, sure. There's two reasons we're doing home first. So I'll start with the simple one, which is just generally very disruptive technologies and products never enter top-down into enterprise successfully. So even if you look at the newest wave of AI with respect to LLMs, like ChatGPT, for example, didn't succeed in enterprise. OpenAI tried for a long time to get their models rolled out in enterprise, but like, good luck getting through like risk-averse CEOs, IT departments, red tape, labor unions, like, not going to happen. So in the end, they released it to the public. Everyone loved it. Everyone figured out creative ways to use it. They brought it to work, and again, they got like, no, you can't use this at work. But over time, it's just like the productivity increase of using this tool is so high that it creates so much bottom-up pressure that enterprise has to adopt it. And that's happened now, right? So now they're doing great in enterprise.
Right.
We had the exact same experience in robotics. We deployed our previous product, and we went through the same thing. Like, product is great, customers are happy, we're saving them money, it's a better service, but man, does it scale slowly because of all of these resistances. By going through the home, you can ride the consumer adoption wave, right? Look at the adoption of iPhone throughout society, how fast that happened. And that only happens in consumer. This creates bottom-up pressure, which is very, very needed in humanoids right now, so that people figure out how to use this, not just for their higher quality of life at home, but in general to like get better margins at whatever they're doing with their small businesses or whatever. This becomes like entrepreneurs starting to figure out how to use your system.
Right.
And that bottom-up pressure will drive mainstream adoption into enterprise over time, so that you get to where this is deployed as a general labor solution across society, not just in homes. So that's the kind of like, I'd say like the obvious one. Now the second part is not as obvious. And that is that, I like to say there's almost some poetry in it. Intelligence comes from diversity of thought and diversity of experience. And this is extremely clear now from everything that's been happening in large language models to everything that we've seen in our own systems as we train our big foundation models based on our robotics data. That the difference between a pretty good model and a great model, and hopefully an even better model approaching proper intelligence, is not mainly scale, it is mainly the diversity in the data. And I like to say, like, if you want to some extent this is obvious in hindsight, right? If you want to figure out how to use a washing machine to wash your clothes, if you've seen 1,000 different washing machines in different environments, you start to get the general concept of what a washing machine is. It's like it's got this round hole that it's the door on this, and there's probably some hinges somewhere so I can see where it opens, and it opens up so I can put the clothes in. If it doesn't open up, there's probably a button somewhere here. If that doesn't work, maybe I need to put the dial back to 0 before I open it, right?
Right.
This comes from the diversity. This does not, sorry, this does not happen in factories. In a factory, you install a robot, and then 5 minutes later, you don't need more data from that robot because you have enough data of that one task. And we see this now that we need a few minutes of data from each task,
right?
And then it saturates. So it's all about how can you get as many tasks as possible, as diverse an environment as possible. And that is basically integrating these androids into our society, living among us, doing tasks among us. And nothing is more diverse than a home. Every home is different. And not only is every home different, every home is different every day, right? So like, it's counterintuitive because that's the highest complexity you could try to tackle. But that entropy or complexity is actually where intelligence comes from. So if you want to get your systems to actually be intelligent enough to solve real problems, you have to start in the home, and then as you get to machine intelligence, you can deploy this broadly across all sectors with respect to general labor.
Right. Talk a little about how training has changed with LLMs and with kind of these latest advancements in AI. You know, ChatGPT busted on the scene for most people a couple of years ago. How has inference learning and some of these new learning methodologies change the way that you can get to and feel comfortable putting a robot in a situation that you know changes every single day and knowing that you're going to be able to catch up on the learning. How does that really change the deployability of these things?
I think first it's just important to create like let's just create a baseline for what the product is. So, I can't tell you exactly when, but it's before people think. When you have this at home, there's a mix of systems that's at play here. There's the autonomy, which is the companion, where you can talk to the robot, it responds to you in a natural manner, there's body language, there's pure magic in this actually. It's like incredibly engaging, and a very good interface for how to interact with modern big AI models, which generally has not been figured out yet, right? It's kind of clunky to do in like a text format or on your phone. And then there's the tasks that the robot does, like go and get you something, or tie to the table, or all these things. And seamlessly kind of blended into this, there is some teleoperation. So there's a human operator that can help the robot cover things that it does not know how to do, so you get the data so you can automate it. And this is how you kind of bootstrap your way into this type of
operator to cover quarter cases, basically.
Yes. And usually not just through a keyboard, but through a teleoperation system where we map a human's body to the robot's body. So you actually do the task just as you were there. It's actually a kind of magical experience. It feels like your hands and like you're somewhere else doing something. And
you're training it in the operation of that function.
Yes, that's the training data, right? So training data is a mix of everything that just happens, where there's a lot of autonomy, plus these what we call the expert demonstrations, where a human actually takes over and does some tasks because we don't have enough data to start to automate this yet. And this is how you move from like the small data regime, which we're currently in robotics. So even with having like the biggest data set on the planet for humanoid robots, it's still tiny compared to like what is used to train a modern big language model like GPT-4. And we need to kind of get our way out of that low data regime into the proper at-scale data regime with this incredible diversity in the data set if we're going to get to proper machine intelligence. And what really excites me is that we see that when we're doing these things, we not only do we solve what I like to call like physical intelligence, we also see that so much of our actual intelligence comes from the physicality. And I'm super excited to see how many of the problems that we currently see in how to get to the next better models in digital AI will actually benefit from the work we're doing on the physical side. Because really understanding how the world works is instrumental to how you reason. So when we think about modern big models reasoning, a lot of the gaps there comes from the lack of the ability to ground your reasoning in the physical reality. And yeah.
That's great. So we're running out of time, and I could go for hours, but we don't have hours. But I want to ask kind of how you first got into this. And you mentioned in another interview I saw getting ready that early on you did a lot of work with elderly people and helping elderly people. What was that experience like? What was it about doing that was part of your motivation to create this company?
Yes, this is a good call out. So I think like very short version of that story is, right, when you have a job like I had then, was just side gig to college, and you're supposed to go help someone clean their home because they're not able to do it themselves. And for most of the people I come to, they've already done it. And it's like a struggle for them, right? There's a reason you're supposed to help them do it. But they've done it just so you can sit down and like have a cup of coffee and talk to them. And I think this is like a gross misuse of human resources, right? Humans should be used for what we want to use humans for, which is human connection. And we should free ourselves from basically menial labor. And I think there are two paths to this. One is we want to free up time so we can actually give people dignity as they age. But the other one, which I think is equally important, is we want to enable, all the way out to some kind of artificial life, companionship through AI. And this companionship needs to be embodied. It needs to help you do physical tasks. It needs to be part of your life to help you leverage this increased work output to make your life better. And I think that can really, really change how we as a society see independence as we age. And this is increasingly going to be important as a large part of our demography ages, right? But I do think it's not just about saving labor. I think it's actually a lot about providing independence and companionship, right? You want to go out and see your friend, now you can like get dressed when you want. You can get help to do that. You want to get out of bed when you want to, not when someone comes over to help you. You want to get food when you're hungry, right? And being able to do this in an independent manner is also really, really important to both your physical and mental health.
Right. And did you see that with Eve? Did people blend? Did people blend kind of the conversational, I need companionship, with the, oh, by the way, can you take out the garbage, or whatever the tasks were? I mean, and kind of this kind of natural blending of human to human interaction that is both conversational as well as task-based.
Kind of saw the beginning of it, and like that there's magic there, but the system wasn't good enough yet with Eve. So this is one of the things that I'm super excited that we're now exploring with Neo. The ability to not just do the physical tasks, but to be a companion and do these physical tasks in a manner that is not just effective, but also pleasing to you in the way you want to do them. And again, back to the diversity, right? Everyone wants their tasks done slightly differently, which again is super important for you to learn.
Right, right. All right, Bernt, well, thanks for spending some time. Congratulations on Neo. We can't wait for it to hit the market. I know you can't say when, but hopefully sooner than we expect. And it's small, it's soft, it's comfortable, and not dangerous. So congratulations, and can't wait to see it in the field.
Awesome, thank you.
All right, he's Bernt, I'm Jeff. We're at Humanoids Summit in Mountain View, the inaugural one. Thanks for tuning in. We'll catch you next time.